Welcome back. My name is Cédric Notre-Dame. I'm a researcher in bioinformatics. This week, I will give you an overview of the main databases in bioinformatics and explain the kind of data you can access in these databases. With respect to medical genetics, there are roughly two kinds of databases. The medical ones that describe the disease and the mutations causing them, and the generic databases that contain the original data, typically the full genome. We will start today with the medical databases, and during the next lecture, we will see what are the core generic databases used in bioinformatics. This week will therefore be pretty much focused on data. In the medical world, the most frequent reason to access bioinformatics resources is to better understand the molecular basis of a disease. This knowledge can be useful to either establish a diagnosis or to refine it. It must also be stressed that the databases containing this information are free and easily accessible. In many cases, their high-quality content can be understood by anyone having completed high school and having basic notions of genomics. It means that, often enough, your patients will already have this information and they may seek clarifications. For instance, it is well known that in the case of rare diseases, patients often know the medical literature as well as the physicians. It is therefore important to promote these resources because they provide a useful reference, especially at a time when countless websites promote dangerous medical advices. At the same time, it is important to point out that these websites often provide scientific evidences whose medical relevance may not be straightforward or may be even counterintuitive. For this reason, the first resource I have decided to introduce is the Genetic Home Reference. This database is accessible via a website and it is meant to provide information for the general public about the effect of genetic variation on human health. It is most likely to be the database your patients have looked at before coming to see you, or the database they will look at after receiving a diagnostic. This database is maintained at the highest scientific standards by the National Library of Medicine staff, and its content is updated on a weekly basis. As you can see on the entry displayed here, it provides high-quality information without any jargon, but it will nonetheless link to valuable scientific information such as gene name and mechanisms. For instance, when looking for breast cancer, we get a very high-level description of the disease and a list of genes known to be associated with a higher risk, including, of course, BRCA1 and 2. But where do all the gene names come from? And is there a place where we can find them? Of course, the answer to this important question is yes. And the place of reference is the HUGO Committee database. HUGO is a Human Genome Organization. Why do we need HUGO? Well, as we all know, the way we name things in science is extremely important. This issue is especially critical with gene names. Bear in mind that genes were originally defined as segregating characters. Mendel or Darwin knew nothing about DNA. Yet, while the relation between genes and DNA is now firmly established, the exact mapping between phenotypes and their causal underlying genetic variations can be extremely complex. As a consequence, many genes were independently discovered more than once in different conditions, and they were named accordingly with different names. This has resulted into a lot of confusion in the scientific literature and prompted a famous geneticist, Michael Ashburner, to remark that scientists would rather share their toothbrush than their gene names, meaning that when two publications report the same gene with different names, it can be very difficult to convince the community to use only one name. Fortunately, things have improved a lot, at least for human genes, and the HUGO Gene Nomenclature Committee is now in charge of approving unique and meaningful names for every known human gene. This is done in collaboration with experts in the field. In addition to the name, which is usually 1 to 10 words long, the HGNC also assigns a symbol, a short group of characters, to every gene. This symbol is unique and non-ambiguous and can be used in replacement for the long name. For instance, if we look for BRCA1 on the search page, we immediately find out that BRCA1 is a unique identifier of the gene named BRCA1 DNA repair associated. And we incidentally find out that in the literature this gene has had other names like protein phosphatase 1. These alternative names can matter. For instance, in the case of a rare disease, it may happen that an older case study refers to a non-standard name for that same gene. It is important to have in mind that HUGO is the only authoritative reference when it comes to gene name. Now that our genes have been named, we need a resource linking genes and diseases. The genetic home reference is a great starting point, but in order to properly integrate everything that is to be known on a gene, a more complete resource is needed, the OMIM database. OMIM means Online Mendelian Inheritance in Man. And it is really what it says on the box, a comprehensive, authoritative compendium of human genes and genetic phenotypes. OMIM is available for free and updated on a daily basis. OMIM describes all known Mendelian disorder, that is to say, diseases caused by the alteration of a single gene. For each of these traits, OMIM reports all the disorders whose variations have been shown to have phenotypic effect. In total, 15,000 genes are now included in OMIM. You will use OMIM as you will use any online reference database. For instance, if we type in the search window breast ovarian cancer, we will get a list of all the entries associated with this disease. As you can see, we get many entries because many genes have been shown to be associated in various ways to this disorder. Some entries are dedicated to a disease like breast ovarian cancer susceptibility type 1, while others are dedicated to a gene, like for instance the BRCA2 entry. If you click onto the BRCA2 entry, it will take you to the corresponding page that will link to all the disorder, mostly cancer, associated with variations in this gene. If you click on breast ovarian cancer type 2, you will reach the entry describing this cancer. Note that these entries are produced by curators, and as a consequence they will not be always up to date and may not integrate the latest literature. On the other hand, manual curation ensures their very high quality. At that point, you may ask, what is the situation with the more complex genetic diseases, the ones for which family history shows an existing pattern, but for which the culprit is a complex combination of genes? These are named polygenic diseases, and the resources and methodologies associated with their study will be covered later in the genetic module. OMIM is not the only available resource linking human genetic diseases and their causing gene. Several other databases are available that attempt to record disease-causing or disease-associated, in other words, pathogenic variations. These include the Human Gene Mutation Database, ClinVar, DBSNP, LoveD, and the Locus Specific Mutation Database, LSBD. All these databases somehow claim to be more complete on specific aspects, yet the bottom line is that they are all based on manual curation. As a consequence, the data they contain is to some extent interpreted. But most importantly, it is as complete as might have been achieved at the time of curation. In practice, this means that the practitioner should consult all these resources and always consider the possibility that more recent evidences may be available on a given disorder. For this, PubMed is your best friend, and we will finish with a few words on this database. As you know, there exist many types of different mutations. Some, the ones we are most familiar with, include the change of one base by another, or the insertion or deletion of a few nucleotides. These are named single nucleotide polymorphism, SNPs. The others are more complex, and they involve longer insertions, deletions, and even fluctuations in the number of copies of one gene. For instance, you may have 5 copies of a given gene and someone else 3 copies of the same gene. It is only recently that it became clear that such structural variations were very common and probably play an important part in our genetics and our diversity. For this reason, they get their own dedicated database, DBSNP, for the single nucleotide mutations and DBVAR for the others. It is also worth stressing that even though their content tend to be similar, the philosophies of these databases are a bit different. For instance, OMIM is a disease-centered database and will therefore be as complete as possible with respect to the number of diseases it covers. But it may not include all the rarest variants, and some may only be available in DBSNP, DBVAR, or even in CleanVAR. So, time to wrap up. What we have seen today is that powerful resources exist to explore the links between diseases having a genetic cause and the genes likely to be involved. These resources are very important, but bear in mind that they're being fed with fast-growing data. As shown on this figure, the number of mutations associated with germline diseases is increasing very fast. In practice, it means that you will need to always consult the latest version of these databases, and it also means that you will need to consult all the databases to make sure you do not overlook anything critical.